Previously, we have discussed the proper way to solve conservation laws, that is finite volume. And we discussed what is the proper way to reconstruct the flux using only the cell averages. In the beginning, we tried a central flux, which didn't work at all for shock waves. Whenever we get a shock wave, we create wild oscillations if you just take the central flux approach. Okay. And then we decided to use an upwinding flux, which produced the correct behavior around shock waves, but didn't always produce a physical solution. And then we introduced the entropy condition. Right? The entropy condition says that the characteristic lines can run into discontinuities, but they cannot emerge from discontinuities for physical reasons, because physically there is always an infinitesimal viscosity there that is going to smooth out, that is going to expand any discontinuities where characteristics can go out of. Right, it'll instantaneously make that discontinuity no longer a discontinuity. While if you have characteristics running into a discontinuity, that counteracts with a very small amount of viscosity and maintains that discontinuity. So we discussed what is the proper way to solve equations and to get solutions that are physically correct. That leads us to the derivation of the Godunov scheme. Okay, the Godunov scheme looks at the correct flux at t plus epsilon. It solves a discontinuous problem for infinitesimal amount of time analytically and look at the flux after that infinitesimal amount of time. And that is the correct flux to use. Right, so these are what we discussed over the last lecture, but we found that all of these is going to only give us a first order scheme. So in this lecture, we are going to discuss how do we get more than first order schemes using the physically correct numerical flux, the Godunov scheme. The key to that lies in reconstruction. Let's draw our solution as a function of x at a particular moment. So in finite volume, we have the cell averages. So let's represent the cell averages using piecewise constant lines. And it is exactly this piecewise constant solution that we used in our Godunov numerical flux in the last lecture. We looked at this discontinuous solution over here and see how it will evolve after epsilon amount of time and what is the flux after epsilon amount of time at that interface. The reason why it is only first order is not because of the way we are computing the flux, but because of the way we are looking at the solution. We are reconstructing the solution only up to first order. It's a piecewise constant reconstruction. In this lecture, we will still use the same numerical flux, but reconstruct the solution in a more accurate way. We want to produce a second order reconstruction. We want to produce a second order reconstruction not just by connecting the two cell centers, because if we do that, we get back to our central flux scheme, which we know doesn't work for shock waves. What we want to do is we want to reconstruct the scheme to second order using only information from one side of the interface. We want to extrapolate instead of interpolate. So for example, if I'm looking at this interface, over here, I want to reconstruct the left-hand side of this solution by using only the cell averages over the left. For example, I can produce a reconstruction by connecting these two centers, and here is my reconstruction from the left. I want to reconstruct information from the right using this information and this information, for example, connecting these two dots. That will allow me to reconstruct a solution over here. this is going to ensure that if the wave travels towards the right, using good enough numerical flux is going to compute the flux according to the left-hand side solution here. If the wave is traveling towards the left, the good enough numerical flux is going to compute the flux using the right-hand side solution here. So we're still using the upwinding side of information, which is physical, but we have a construction that is second order. All right. So here I'm drawing a very discontinuous solution over here. But if you imagine I'm doing the same reconstruction over here, over a smooth region of the solution, then I'm going to be doing a really good job. By connecting these two, I get a solution here. By connecting these two, I'm getting a solution here, which really gets us a good reconstruction. Okay, so this kind of extrapolation from only one side gives us the correct behavior around shock waves and a very accurate reconstruction in smooth regions. Okay, so this is the approach we are going to be using here. So we are constructing U. So let's say this is the ith cell average. This is the I plus 1th cell average. We are going to reconstruct U at I plus half on the left using information on the ith grid point and I minus 1th grid point. We are going to reconstruct the solution at the same grid point, but at the same interface, but immediately towards the right of the interface using Ui plus 1 and Ui plus 2. And my flux at I plus half is equal to, let's imagine we write a function that computes the Godunov scheme. That takes two inputs. It takes the left value and the right value. Both are reconstructed from two cell averages. So I end up computing the flux using the 4 cells instead of 2 cells. And that gives me a more accurate second order solution. So how do we perform this reconstruction is what we are going to be discussing today. Okay. The most obvious way of performing the reconstruction is a linear extrapolation. So linear extrapolation means looking at the value at these 2 cell averages and linearly extrapolate to here and linearly extrapolate to here. So we can do that. Unfortunately, it is going to create the so-called Gibbs phenomenon. So Gibbs phenomenon is something you observe around discontinuities where you have artificial oscillations going on. So the typical Gibbs phenomenon is when you should have a discontinuity like that, you observe something like this. All right, so this is the so-called Gibbs phenomenon. And the reason you have this is because this reconstruction here and this reconstruction here around any large discontinuities creates a large overshoot and undershoot, right? And this violates the correct behavior of a scalar conservation law, which diminishes the total variation of the solution. Remember the total variation? The total variation is defined as an integral over a region a to b, the absolute value of the derivative integrate over dx. And numerically, it is equal to the summation goes from I to I1 to I2. So this this is summing over a range of grid points. And instead of derivative, we have u of I minus u of I minus 1 taking the absolute value. So this is the discrete analog of the total variation. Instead of taking the derivative, you take the difference between two grid points, and you can divide by delta x and multiply by delta x. It's going to be the same. It's a discretization of the total variation, right? Just count how much change has happened when you walk through the sequence of grid points. So we want this total variation to decrease monotonically, at least not increasing when we time integrate the solution. If we create this kind of overshoot when we reconstruct the solution, then the total variation increases because I'm creating new extrema, new minimum, and new maximum. I'm potentially increasing the local maximum and decreasing the local minimum through the reconstruction. And that's what we want to avoid. Any questions of what we want to achieve? Oh, it should not increase as you time integrate forward. So the total variation, it's a good question. So the criterion is the time derivative of the total variation is less or equal to 0. So we want this to not increase over time, not as I decrease. So that's the correct behavior for scalar conservation laws, because in smooth regions, the solution follows characteristics. So any minimum or maximum is conserved. If there is no discontinuities, the time derivative of total variation should be 0. Right? Because the solution is morphed in shape, but like it never changes its shape. So any monotonically increasing regions, it's still going to be monotonically increasing. It's just the bounds of the region are shifted over time. Any monotonically decreasing regions are just shifted in space. Yes. So the question is, can you think of the Gibbs phenomenon in terms of Newman stability analysis? You can think of the Gibbs phenomenon as a result of dispersion error. So dispersion error moves waves to incorrect places, and this results in the oscillations over here. And this is most obvious around shock waves, because around shock waves you have very high frequency content of the solution. So if you have dispersion error, you are moving these high frequency contents to wrong places, to places away from the shock wave. All right. And also, most time when we have a discontinuity, that's when we have a nonlinear conservation law. We have characteristics running into each other. If you have linear conservation laws, all the characteristics are parallel to each other, and you rarely have discontinuities that are as sharp as that. So the objective in this lecture is to reconstruct the solution to second order accuracy without overshooting.